Have you ever wondered if the universe's rules can be bent? What if, hidden in the tiniest corners of life, there are rebels quietly challenging everything we think we know about how the world works? We're taught that Newton's laws govern everything, from the majestic dance of planets in the vastness of space to the simple arc of a baseball flying through the air. These rules seem unbreakable, shaping the motion of everything we see and touch. But what if something as tiny as a human sperm cell could break those rules? Imagine a world so small, the usual laws of motion start to blur, and new possibilities emerge. This isn't science fiction, it's a real, mind-bending discovery happening inside us all the time. Deep within our bodies, these microscopic swimmers are rewriting the rulebook of physics. Imagine a cell so small it moves forward without pushing back, like a canoe gliding across a lake without ever dipping its paddle in the water. It's a motion that seems impossible, yet it happens every second. The secret? It lies in the strange world where biology and physics collide, a place where the rules we learned in school don't always apply. Here, the boundaries between living things and the laws of nature become blurred. This tiny swimmer's trick could revolutionize medicine, robotics, and our understanding of life itself. By learning from these microscopic rebels, scientists are dreaming up new ways to design tiny machines that could one day heal us from the inside out. For centuries, we thought sperm swam like tadpoles, pushing against fluid to move. It seemed obvious, just like a fish or a frog. They'd wiggle their tails and propel themselves forward. But when scientists looked closer, using powerful microscopes and new technology, they found something that didn't add up. A secret to motion that defies our intuition and challenges our understanding of the natural world. Let's dive in and see how the smallest things can teach us the biggest lessons. Sometimes it's the tiniest rebels that spark the greatest revolutions in science. To truly grasp the sperm's unexpected behavior, let's take a step back and revisit one of the most fundamental principles in physics, Newton's third law. For every action, there's an equal and opposite reaction. This isn't just a rule for rockets or machines, it's a law that governs almost everything we see and do. This law explains why rockets soar into the sky, why we're able to walk across the ground, and how birds take flight. Every movement, big or small, is a dance of forces pushing and pushing back. Imagine you're on a skateboard and you push against a wall. Instantly, you roll backward. The wall pushes you away just as hard as you pushed it. Or think about swimming in a pool. You push the water behind you, and in return, the water pushes you forward, propelling you ahead with every stroke. This principle is so universal, it's the very foundation of classical mechanics, the science that explains how things move. For centuries, scientists and thinkers believed that nothing could move unless it pushed against something else. It was a rule as solid as gravity itself. Every action, every movement comes with a cost, a push in the opposite direction, a reaction that balances the equation. So, when scientists first observed sperm swimming under the microscope, they naturally assumed it was just another example of Newton's law at work. Tiny swimmers pushing against the fluid to move forward. But then, something strange caught their attention. The way sperm moved didn't quite match the expected pattern. Their swimming style was different, almost rebellious. Sperm seemed to glide forward without the usual pushback, as if they were breaking the rules of physics we thought were unbreakable. This surprising discovery challenged everything scientists thought they knew about motion at the microscopic scale. Suddenly, the microscopic world wasn't just small, it was strange, unpredictable, and full of surprises that defied our expectations. Science becomes truly fascinating when the rules we rely on start to bend or even break, forcing us to rethink what we know. And that's exactly what happened here. The sperm's movement opened the door to a whole new way of understanding the hidden rules of life. Let's zoom in on the human sperm cell, a marvel built for one purpose, reaching the egg. It has a head full of DNA and a tail called a flagellum, its engine. But the world it swims in is thick, like honey, not water. For something so small, viscosity dominates. If it stops moving, it stops instantly. Scientists once thought the flagellum worked like a whip, pushing fluid backward to move forward. But as microscopes improved, they saw the flagellum's motion was more complex, almost corkscrew-like. The movement was too efficient, too graceful for a simple whip. This was the first clue. The sperm's tail was hiding a secret. It wasn't just about pushing fluid. Something else was at play, something classical physics couldn't explain. The sperm cell was about to rewrite the rules. Scientists put sperm swimming under the microscope, literally. Teams from Kyoto and Oxford mapped the flagellum's movements and the forces in the fluid. They expected Newton's law to hold. Every push from the tail should have an equal pushback from the fluid, but the math didn't add up. The sperm moved forward more than it should have, as if getting a free push. It was like a magician's trick, motion without a matching reaction. The scientific community was stunned. The sperm seemed to exploit a loophole in the laws of motion. Newton's laws still worked for planets and swimmers, but at this tiny scale something new was happening. The answer wasn't that the law was broken, but that it was incomplete. The flagellum's material had properties Newton never imagined. A new kind of physics was at play, hidden in plain sight. The secret behind the sperm's remarkable swimming ability? It's something called odd elasticity, a concept that's as fascinating as it is unexpected. Most of us are familiar with regular elasticity. Think of a rubber band. You stretch it, and it snaps right back into place. Or a spring. You push or pull, and it returns to its original shape. This is the classic push-pull give-and-take behavior we see in everyday objects. But odd elasticity is a whole different story. Instead of just bouncing back, when something with odd elasticity bends or stretches, it creates internal forces that twist, rotate, or push in directions you wouldn't expect. It's as if the material has a mind of its own, responding in ways that defy our usual intuition. Imagine pulling on a rubber band and instead of just stretching, it also tries to twist itself sideways, almost as if it's trying to wriggle out of your grasp. That's the strange world of odd elasticity. The sperm's flagellum isn't just a flexible whip, it's an active structure, packed with molecular machinery that gives it this odd elastic property. As the flagellum wiggles and undulates, it generates forces that don't simply push back in the opposite direction. Instead, these forces can twist and propel the sperm in ways that seem to break the usual rules of motion. It's a bit like watching a snake slither forward on a perfectly smooth, frictionless surface, using clever, coordinated movements to move ahead, even when it seems impossible. But don't be fooled, the sperm isn't breaking the laws of physics. It's still obeying the conservation of energy. What's really happening is that it's using energy in a highly sophisticated, almost ingenious way, channeling it through its flagellum to create these unusual forces. Chemical energy stored within the sperm is converted into motion. This energy powers the odd elastic forces, allowing the sperm to swim efficiently through thick, sticky fluids that would stop most other cells in their tracks. Over millions of years, evolution has fine-tuned this remarkable material, engineering the flagellum to solve the unique challenge of swimming through viscous environments. The flagellum isn't just a simple paddle, it's more like a microscopic engine, a self-propelled machine that uses bizarre, counterintuitive physics to get the job done. This clever loophole in classical mechanics lets sperm swim forward, even when the usual rules say it shouldn't be possible. In the end, nature found a way to outsmart the rules, using odd elasticity to turn a simple tale into a marvel of microscopic engineering. Sperm aren't the only ones with this trick. Scientists studied Chlamydomonas, a single-celled green alga with two flagella. Using the same techniques, they found the same odd elasticity at work. The algae's flagella propelled it forward without a perfectly balanced pushback. This wasn't a fluke, it was convergent evolution. Both sperm and algae evolved the same solution for efficient swimming at microscopic scales. This means odd elasticity is a powerful fundamental strategy in nature. Studying algae, which are easier to grow in labs, helps us unlock even more about these smart biological materials. Nature's weirdest physics is more common than we thought. Why does this matter? Understanding sperm swimming is crucial for fertility science. If the flagellum's odd elasticity fails, sperm can't reach the egg, so this could help diagnose or treat infertility. It could also inspire new contraceptives that safely disrupt sperm movement. Beyond medicine, this discovery is a game changer for robotics. Engineers can mimic odd elasticity to build tiny robots that swim through the body or clean up pollutants. Imagine microscopic machines powered by nature's blueprint, revolutionizing healthcare and technology. By learning from sperm and algae, we can design smarter, more efficient machines. This isn't just a biological curiosity, it's a roadmap for innovation. The possibilities are vast, limited only by our imagination. Sometimes the smallest discoveries have the biggest impact. Odd elasticity opens a new world for engineers and scientists. We can now design metamaterials, active materials that move, change shape, or even compute inspired by biology. Imagine ship coatings that actively reduce drag, or surfaces that cancel noise by generating their own vibrations. The logic of life is being applied to machines. Our scientific models must evolve too, adding odd elasticity for more accurate simulations of cells and bacteria. This accelerates research in medicine, energy, and beyond. The discovery was only possible through interdisciplinary teamwork: biologists, physicists, mathematicians, and engineers. The biggest breakthroughs happen at the boundaries between fields. By combining different perspectives, we uncover secrets hidden in plain sight. The future is built on curiosity and collaboration. What's the takeaway? Science isn't a fixed set of rules, it's a journey of discovery. Odd elasticity doesn't mean Newton was wrong, it means the universe is more subtle and weird than we imagined. Every time we think we've figured it out, nature surprises us. These moments drive science forward and inspire new generations. The sperm cell's story reveals hidden complexity in the simplest things. From a basic question about swimming, we found a discovery that could reshape technology. Science is about curiosity, asking questions, and embracing the weirdness of nature. There are still countless mysteries to solve right here on Earth and inside our own bodies. So next time you think of physics, remember the tiny sperm cell and its lesson. Stay curious and expect surprises. Because the next big discovery could come from the most unexpected place.